Hello, this is Tommy. Welcome back to Genomics. In today's video, we will continue our journey of replicating a published genomic paper figures. So if you haven't watched the previous video, make sure you watch the videos in the same playlist to get an idea of what we are talking about. So in the previous videos, I have shown you how to download FASTQ files and to do quality control, align the FASTQ files to the genome, so it's a ChIP-seq data set, and then how to actually make a big wig file to visualize on IGV and how to call peaks using Max3. So once we have all those files ready, those pre-processing steps done, so we're ready to replicate the figure in this genomics paper. Okay, today's video we will actually reproduce figure 1, A, B, and C. As you actually watched probably one of my previous videos, that when you see a figure, you need to do some analysis. First, what kind of plot type is that, right? So look at A, B, and C here. So the plot type here is a Venn diagram for A and B. And for C, it's just a line plot. And once you identify what kind of plot it is, for example, for figure C, you need to figure out, okay, what's on the x-axis and what's on the y-axis, and what data are needed in order for you to make those figures, right? And for the Venn diagram, essentially, you just need actually two numbers, and essentially three numbers, okay? The set A, set B, and the intersection. And that's how you make a Venn diagram. And you can use many R packages to make a Venn diagram. And for figure C here, if you look at it here, so the x-axis is the distance to the summit of the TAS1 peaks. So TAS1 is one of the transcription factors that they provide using ChIP-seq. And then the y-axis is the peak density of so it's in the position of the TAT4 peak summit, okay? So essentially, you looking at the TAS peak summit, and you look at the TAT4, this, the other transcription factor, the summit along the summit of TAS, and then across all the peaks, then you can essentially build the line graph. So I will show you how to do that in R. But first of all, how do you get those numbers for Venn diagram, right? So you get the peaks number for YAP and TAT, you get the peak number for YAP, TAT, and TAT. So essentially, after peak calling, you get all those peaks, and it's a matter of just finding the intersections. And there's a command line tool that is really powerful, and you should learn how to use it. It's called BEDTools. So BEDTools is a command line tool, and that is designed to do all sorts of genomic interval manipulations. And BEDTools intersect is one of the most commonly used command. So I have a link here, then you can go to the website and read all the tutorials or the menus of each different subtools. But BEDTool intersect is one of the most common one that you can use. So in our case, for ChIP-seq data, you identify a peak set of A here, like multiple regions in the genome. And then you have a peak set B here for a different transcription factor or histone modifications. And then you can use the intersect A and B to find intersections, right? And depending on the flags or different arguments you turn on, for example, you use WA, and then all the regions in A that has overlapping with B will be returned, rather than this gap, the region. So, and if you use -V, it will be the reverse. So it will only return the ones that is not overlapping of any regions in B, okay? So what you can do here, okay, let's show you how to do that with BEDTools. So you can install BEDTools using Conda. Conda install BEDTools usually should work for you, okay? And I have already installed it, and let me go to the folder which contains the peak files. So cd data, and it's in the FASTQ folder, and the peaks, they're all in these three folders, okay, the peak number. So if you look at file inside, you have this narrow peak file. Okay, and if you look at the other one, YAP1, and you have this peak file. So those are just like a regular text files. You can look at the lines first, a couple of lines. Oh, so you need the full path here, the peak, and then the file name here. So I'm going to look at the first 10 lines here. So essentially just a regular text file. There's a BED file format with 3 columns here, like this is the most important one, chromosome, start, end, the name, and some other columns. So make sure you read my previous video to explain what those other columns are. Okay, so what you can do here, so look at here, so we can do BEDTools intersect A and dash B, and then there's 2 peak files, and then use this arguments, and then it will return only the ones that is overlapping with B. But then I need to sort it and then look at the unique. So for example, if I don't sort and do the unique, how it looks like. So if you do this, you have actually 7,199 task peaks that is overlapping with the YAP1 peaks. Okay, but if you look at it, this will just return you all the peaks in A that is overlapping with B. But if you do this sort first and unique, and you only give you the unique rows, and you do word count dash line, you get how many lines there, you actually find there are actually roughly 45 lines less than this. This is because some of the peaks here, like for example, a single peak can overlap with multiple peaks in this peak set. And this one, the ones that are overlapping with multiple peaks in the second peak set is getting duplicated. So that's why you want to actually, if you want the unique number, so you want to pipe it to sort and unique and get the number of peaks. So it will be 7154, okay? Okay, let's go back to the okay. So that's how you do that actually with BEDTools. Okay, but let's just be consistent and do everything in R, and I will show you that essentially R will give you the same results. And in order to do that, we will use this package called Genomic ranges in R. Okay, and I have an actual blog post of why this genomic ranges package is so useful, and this is a data structure in R that is commonly used to deal with genomic intervals, and you don't need to reinvent the wheels to deal with them. Okay, so let's load the library. So if you don't have the library, make sure you install it from Bioconductor, BioC, Manager, Install, and the package name. And RTrack layer is also a Bioconductor package, and you can use that to read in the peak files. And here package is just to give me the full path of that file. Okay, so you can import the task peaks, and you import the YAP peaks. Now, if you look at this, it just gives you the genomic ranges object. This total number of peaks for this. If you do this, for the second one, is almost 10,000 peaks for YAP1. Okay? And you can use this function called subset by overlaps. And this peak set 1, peak set B, and this will give you the task peaks that overlap with YAP peaks. If we do that, we give you some warnings because there's some unconventional chromosomes that is present in one of them but not in the other. We'll ignore them for now. So if you look at this, this is still the the task peak overlap with the YAP1. So if you look at the length, so you have 7154. It's the same as what we get from here. Okay. Okay. Now so we can actually also do the reverse, right? So we can look at task 1 that it has that overlap with YAP, but we can also do YAP overlap with task. You just switch the order here. So if you do this, and then again look at the length, now it's 7164, and you notice that these two numbers, they are not the same. I mean, ideally, if you think about a Venn diagram, right? A set B set the intersection, and the intersection should be the same. But in this case, this is peaks. So because you have one, it's possible you have one peak overlap with multiple peak in one of the other sets. So that's why it's not the same. Okay. So as I say here, we have this many out of this many task peak overlapping with YAP1. Then we have this many out of this many YAP1 overlapping with task peaks. So, but the Venn diagram needs a common number in the intersection. How do we deal with that, right? So there are different decisions you can make, and doesn't it really affect the conclusion of the figure, which is most of the task and the YAP1 peaks overlap. So we can just use the number of YAP1 peaks that overlap with task as the intersection, okay? There are many ways packages to make a Venn diagram. I will use this tool called a Venerable. So you install this from GitHub, and I already have it, so I'll load the library. And now I will get the total number of peaks for each set. This total number. And I will just use the overlap, the intersection as the YAP overlap task. Okay, this is just my decision here. Okay, so this is the 7164 here. And now you can make a Venn diagram. Essentially, you can just 1, 0, essentially, okay, overlapping. I mean, it's only in set 1, but not in set 2, in set 2, but not in 1, and this is common. And this is just the number you specify. The total number of, the total, yes, this is unique to A, unique to B, and this is the intersection. So if you do that and plot, essentially this is the Venn diagram that really you are trying to replicate. Of course, you can always change the color, change the looking, and to make it matching 100% of the original figure. Okay. So you can also use the make Venn diagram function in the chip peak annotation package to do that. So in this case, you only need 2 sets of genomic intervals, right? Okay. Okay, once we have figure 1a replicated, so we can easily just make figure 1b following the same rationale. Okay, so now we look at the task 4 peaks, right? Now actually figure 2 is looking at the overlapping of YAP1 task and then overlap with TAT 4. So we just name this variable as YAP overlap with task and overlap with TAT 4. So what we can do, you can use the YAP, we can do subset by overlaps. YAP overlap TAT. This is the common peak of those two, and then overlap that with TAT 4. Okay, so if we do that, and then we can now get the total number of peaks for each set here. For YAP1 and TAT, common ones, TAT 4, and the number of overlap here. So those are essentially just the 3 numbers, right? And this is the overlap. As I told you, like for Venn diagram, you just need 3 numbers. So now you can use the same Venn function to make the Venn diagram and plot that. Okay, and this is essentially to reproduce this 1b here. Okay. Okay, let's go back. look at here. Okay, so it's the same thing as here in the website, so you can always follow the tutorial here. Okay, now let's look at the figure 1C. That one is a little bit more complicated. It's a line plot, then we need to figure out how to make it. Okay, so what data we need? Okay, the TAS peak set and the TAT4 peak sets, because if you look at here, that's the data we need. Okay, TAT4 peak sets and then the TAS peak summit essentially. Okay, and what's the x-axis here? So when a TAT peak overlaps with a TAS peak, so when you have two peaks overlap, the distance between the summit of the TAS peak and the TAT4 peak summit, so that's the distance. Now y-axis is the number of TAT peaks for each of those distance. Okay, and a summit is just the highest signal point within a peak, and we use the Mach 3 to output that. So let's do that. Okay, so let's input the summit first. So it's also in the same actually peak folder. And if we do this, and look at the summit. Okay, so if you look at summit first, actually, let's redo this. This is just a single data point. So if you look at here, it's a single point for each actually peaks. So that's the point where within the peak has the highest signal. Okay, you see it's just a single point here, and that's for the peak one. Okay, and we will actually only subset the summit that is overlapping with YAP1. Okay, remember, to make that line plot, you need to make sure those two peaks first overlap with each other, and then you calculate the summit distances between these two overlapping peaks. So the name, so this essentially just this name so this, what we calculated before, is the overlapping of TAS peak and the YAP1 peak, and then give the name is the same name here, so you just use that to subset the summit. So for example, now you have like over 10,000 here. After you subset, now you have like 7,054. You remember that's the number of peaks that is overlapping with TAS with YAP. Similarly, we can load the TAT4 summit. If you look at that, it's the same thing. So you have 11,000 is a single point. Okay, so they both represent a single base point that has the high signal in the peaks. Okay, what we can do here, so here you need to actually expand the TAS summit to 500 base pair window. Okay, if you look at the original figure here, so the summit of TAS, and then you expand 250 base pair upstream and 250 base pair downstream. Okay, let's do that. So you just use the resize function with 500 and fix the center. So if you do that, if you look at here, the window here, now it becomes actually 501 actually base pair. So, oh no, actually 500. So total width will be 500, and the center will be in the middle. And you can use this function called find overlaps of the TAT4 summit, okay, with this TAS 500 base pair window to see how many of them are overlap within this 500 base pair window. So this actually gives you a hits object. So essentially those are the indices of the overlapping query and the subject hits. So if you look at here, so it gives you the indices. Okay, for example, this tells you the first in your query, which is the TAT4 summit, overlap with the first in this window. Okay, and then the third one in here overlap with the second one. So it gives you the indices. So what you can do you can use this function called query hits or subject hits to extract those numbers. So if you do this, it will just give you the first column of the indices, and this will give you just the second column of the indices. So essentially give you here and here. Okay, so if you do this, and this will just give you the TAT4 summit. Usually they reorder them according to the quality, the indices here. So if you do this, and this will reorder the TAT summit, which is actually according to the subject hits indices here. Okay, so and then you will actually calculate the distance between those two summits. So if you look at here, and then look at the distance. So this is distances. So essentially, this one and this one, the indices of 1 in this region, and the indices of 1 of those regions, and the distance between those two summit is the distance 6, and then 12 for the next pair, and 18 for the next pair. Okay. Okay. So if you just do a table, it will tell you, okay, how many of them you have. 241. The distance is 0, so the two distances, they are overlapping with each other. 145, you only have like a distance of base 1, for example. Okay, so you can look at the distance, which is equal to 0, and look at the TAT4 actually summit, and it will tell you this. And then if you can look at the TAT1 summit, again the distance equals to 0. Okay, and you can actually verify them. Okay, they're indeed actually overlapping with each other. Okay. Okay, so the built-in distance function returns the pairwise distance in the absolute value, but in the figure it actually gives you a negative or positive depending on whether it's precede or after those two actually summits. So what we'll just need to actually create a new function called sign distance, a and b. So the distance will be a and b, but if a is smaller than b, a is smaller than b, it will be minus. So and then if it's, a is greater than b, it will be actually plus. So distance times the sign here. Okay. So let's create a function. So we can do the same thing. Now we can calculate the summit distance, but now we have a sign. And then we still create the table and then convert that into a data frame. So if we look at this data frame, okay, this is the summit, this is a number. Remember, this is our x-axis and this is our y-axis. Okay. Now we're ready to plot. Okay, distance, ggplot, x will be this, and y will be n, the number of summits that's in this distance. That distance that is between those two summits is minus 249. So if we do that, let's see. Oh, something is kind of weird. What's going on? Because the summit distance on the axis need to be reordered. It should be minus 250, minus 409, and until like to 1, 2, 3 to actually 250, right? Okay. So we will need to actually arrange the summit distance. So we just rearrange from small to big. And now let's replot this. Now you see this is more like a line plot that we see in the figure. Okay. Now we can connect the points. Now it's just dot plot, scatter plot, dot plot here. So but we need to actually just change that into a line. Instead of use geo on point, we use geo line here. We do this, now you will see this. But the plot looks a little bit wiggly, so we can actually smooth it by average the number of peaks per 5 base pair being here. So we can actually just create a new column called a bin, and then equals to the bin equals to the summit distance divided by 5 and times 5. Okay, so I'm creating bins by grouping every 5 base pair, and I'm calculating the mean for every bin here. Okay, so let's do that. And if you look at this, so now we have the average for every 5 base pair bin. Okay, and now we can plot. Okay, now this looks actually much better, right? Because now you have less wiggly line because you actually calculate, smooth it like every 5 base pair using the average for every 5 base pair. Okay, I think that's it for today's video, and I hope you learned something, and make sure you subscribe, and I will continue to finish the rest of the tutorial in the coming weeks. Happy learning.